In the last video, we were discussing about electric potential due to point charges and collection of charges. In this video, we're going to discuss about potential due to continuous charge distributions. That means in the last video, we were discussing about if there is point charges, then what is the potential at P here? We know that electric potential is a scalar. So electric potential is a scalar. That means is a scalar, so you don't have to worry about vector sign, components and everything. You just find what is the electric potential here. Let's say this has a, because q1 has a potential here is v1, q3 has a potential v3, and q2 has a potential v2. So here potential at potential at p will be equal to v1 plus v2 plus v3. That means addition means algebraic addition. That means, so you know, actually when the potential is minus, it will have a negative potential. It has a positive potential like that. So we know the potential of a charge at a point will be k q by r square. Depending upon the value of the charge, potential can be positive or negative. So this is scalar, so doing things is pretty easy than finding electric field. So today what we're gonna discuss here is, so here we're gonna discuss about continuous charge distributions. So continuous charge, you can say that actually for a line there is charges equally distributed over the line, and you can also have a sheet where charges are equally distributed over sheet, right? Or you can think about a disk equally charged equally distributed over disk. In this case, actually we are, when it is coming a sheet or surface area, we discuss about equal charge distribution sigma. That is, if that is equally distributed, we can say that sigma is equal to q by area. If it's a line, and if it is equally distributed over line, then we say that lambda is equal to total charge distributed over the length of the line. So if it is, for example, if it is a sphere, right? It's a sphere. Then if we talk about rho, it is a charge distribution per volume. So charge distribution per volume. So this will be if it's equally distributed over the volume, guess a q over the volume. So whatever it is, if you know the sigma, if you have a small area, if you say dA, so what is the charges on this area, that you can say that small charge dq on that area will be sigma times dA. So if you have a length L, and if you're considering small l dl, well, how much charge is present on this area, this length, this will be equal to lambda, that is the linear charge density per length multiplied by dl. Similarly, if you take a small volume in this sphere, how much is, let's say this dv, how much charge is within this volume, that will be rho times dv. So that is dq over that volume. So we know this before also when we are doing continuous charge distributions in electric field. So in this case here I am considering as an example, I am considering a uniformly charged tin rod. That means we are not worried about the thickness, we are only worried about the length of this, is a small thickness. So here the lambda means charge per unit length, it is equally distributed, so we can say lambda here is q over length. So here I want to find the potential at a point P at a distance d from the line thin rod that is having length L. So in this case we have to choose an element, small element on, let's say I consider a small length dx, and let's say it has a charge dq. We can treat this small element as a point particle. So we have to determine what is the potential that this will create at P, right? So let's say the distance from here to here is R. Then what is the potential due to this small element of charge dq? What is that is creating at this point P? Then if you know that, actually then we get an expression for that. We'll integrate that from starting from 0 to L. Then we get total potential that is being created by the whole charge distribution along this road having length L. So here what we do, we start from here, then we run the integral from x equal to 0 to x equal to L, then we get the total potential at that point P. So here let's come back to this dq here. So let's see what is the relationship here. So dv will be according to point, if we treating this small element as a point particle. So we know by a point particle, point charge, what is the electric field at point P? That is dv. Let's say dv means small potential to the small charge dq, that is equal to k into dq by r. Dq is small charge present at the small length dx. This actually can serve as a point particle as a q for us. dq just represents small charge, dv represents small potential due to this charge distribution dq. So here to get the total potential, what you have to do, you have to integrate from here to here. That is, you have to integrate the small potential over full length of the length. So it will be k dq by r. So what actually we know, lambda is dq by dx. This is just q by x. It's a dq by x, means the charge per unit length. So dq will be lambda into dx. If you multiply lambda with dx, you get the charge present on that length dx. So here look at actually what is r. Here this r is equal to, this is, let's take from here to here is x. So let's say take the length from here to here is x, and from here to here is d. So according to Pythagoras theorem, r is equal to square root of x square plus d square. Then we have to find what is dv. Dv is dq by r. Dq here is means lambda dx. So dq become lambda dx, and r is here square root of x square plus d square, that is x square plus d square. So then to find the total electric potential at P, we need to integrate this from x equal to 0 to x equal to L. So this become k into lambda dx square root of x square plus d square, integrate from x equal to 0 to L. So here we are doing integration from x equal to 0 to L, k lambda dx x square plus d square, square root of x square plus d square. So here you can say lambda and k, because lambda is a constant, because you are considering uniform charge distribution, that means lambda is constant throughout the length. So lambda can be is a constant, k is a constant, we already know, I can take it out. So 0 to L dx square root of x square plus d square. So this value, this integral is a standard integral. So here d is a constant, you can say d is a constant length, d is a constant. So we can look for the standard integral tables that is present for you. So if you find here, you can see an integral, that is integral of 1 by square root of x square plus or minus x square. If it is plus, it will become here plus. So then integration of this, because you are integrating with the length dx, so this is x here, a is a constant. Then what do you get the result of its ln modulus x plus square root of x square plus y square. If it is plus, it will be minus if it is minus here. So using that integral, we will solve this integration. So we have the integral of 1 by x square plus minus x square dx is equal to logarithm of x plus square root of x square plus minus x square. It is here is plus, so we use plus part of this equation. Okay, so what we get actually if you do that, so here we get lambda k, that is already there, it's a constant. So integration of this gives you a logarithm of x, because we are integrating with x, plus square root of Instead of a we have d, that is a constant here, square root of x square plus d square, and you have to run from the length with the range 0 to L. So if you apply L, because this become L, this also become L, the next part actually if minus of L becomes 0, so only then part that is remaining here will be d square. So here we get an if you put the limits, you get the integration result into lambda k uh, into logarithm L plus square root of L square plus d square minus ln d square. So we know logarithm of a minus b is equal to logarithm of a divided b. So here we can use that identity. So we will write this in the form of lambda k logarithm lambda plus square root of L square plus d square divided by d. So this is our final formula for potential due to a line charge that is uniform, that has a uniform charge density lambda at a distance d from the the from the rod. So you get actually v is equal to lambda k logarithms L plus square root of L square plus d square over d. So now as an example, this is so you know what's the benefit of using the what's the main things that is much better in doing potential than electric field is here you have to consider only integrations. You don't have to worry about components and vector signs and vector representations, so this become quite easy if you are familiar with integration. So now there is a pretty another easy example of this is here is a question: a thin ring of radius a lies in a plane perpendicular to the x-axis with the center at the origin O. So ring has a uniform charge density lambda. For an expression of the electric potential at a point on x-axis passing through the center of the ring. So you can think about this. What is given here? This is a ring. You know what is a ring means? If you have a let's say you have a small string, you can convert that into a circle, right? So here let's say you have this string has a equal lambda, that is uniform charge density. If you make that into a circle, that's become a ring. That also all ring, every part you have the equal charge distribution. You know this length of this circle, the length of this string will be equal if there is a radius r, and length, that is a circumference, will be equal to length of the string, that is length will be 2 pi r. So that is I think most of you know understand these things. Now let's, what is the thing here? So at a point from the axis, at a point P, we need to find the electric potential here. So if I consider a small portion here, right, let's say dl, right, the dl will have a charge dq, you know, that will be, if you multiply lambda with that motion of portion of that length, you get the charge there. Then let's say consider that is a small point charge that is having a potential here. So here a benefit of this is, you know, r, let's say this is r is equal to because this become this radius a, this is a length, that is equal to square root of a square plus l square. If you look at here, this a and l will not change even if I move any places here, right? So means r is also remain constant. So I think it's going to be pretty easy integral if you would like to do it. Let's say this dl is producing a potential here. Let's say that is making a small potential TV. We can say that will be k dq by r. So here if you do that here, this will be k dq is our lambda into dl, right, divided by r. So that's dv. Now I need to find total potential here. That means I should integrate from, because you know through the length of this circle. What is the length of the circle? Is if it's 0, then length of circle is circumference of the circle. That is, I told you before, length here, if you convert that into circle, is 2 pi. In radius here, radius is a. So it means I will run from 0 to 2 pi. That means I integrate to get v. I need to integrate dv. That will be integration from 0 to total length of the ring, that is 2 pi a here, and I integrate lambda dl by r. So if I pause here the video, or you can pause here and you can do this integral yourself. So here, that is v is equal to square root of 0 to 2 pi a is the radius, k lambda TL over r. Here TL is only the integrating factor, so this is running from 0 to pi a. Rest of them are constant, because if you look at here, r is a square plus l square. If this l and this l are different, let me say that, for example, let me call this d here to differentiate with that dl that you are doing, d, right? Okay, so you can take another some variable, dummy variable, to represent that. So here let's say this is 0 to 2 pi a k lambda TL, then my r will be equal to here square root of a square plus d square. So you can see k, a, and d square lambda, these are all constant. So let me clean this first. So we were here with dv, that is equal to 0 to 2 pi a k lambda dl over square root of a square plus d square. I call this d square d here, because this r I can say it is a square plus d square, because I took this portion as dl, and that is having a charge dq, that is equal to lambda dl. That's why I convert that, because to distinguish between this length and this length, I use this d rather than l. So here what I do then, I integrate, because I know k lambda and this r is also constant, so that this into anything to integral. So 0 to 2 pi a into dl. So if I dl, that's become l, that will be running from 0 to 2 pi a, so this will gives me k lambda square root of a square plus d square into l, that is running from 0 to 2 pi a. So upper limit is 2 pi a, lower limit is 0, so I get this equal to v is equal to, this is very pretty easy integration, right? Square root of a square plus d square into l, means here l here is, this is l is here 2 pi a minus 0. If I put upper limit minus lower limit, if you look at here, I get the potential here now, v is equal to k lambda square root of a square plus d square into 2 pi a. So this is the final answer, but actually we know k is equal to 4 pi epsilon 0. If you represent that k as 1 by 4 pi epsilon 0 into lambda, here r a square plus d square into 2 pi a. So 2 pi cancel, become that's become 2. So final, in that case it will become lambda a over 2 epsilon 0 square root of a square plus d square. So this is final answer for the potential at point P due to a ring that has uniform charge density lambda. So to another example of continuous charge density is surely this is used to be a surface. So let's consider a surface with a uniform disk. Let's have a distance, sorry, the radius r. We need to find a potential at point P from its axis at a distance so here let's say that you can see here, let me say this length is z from here to here, right? Let me say this length from here is z. So this length r will be equal to square root of r square plus z square. I am considering here a small portion of disk. So I consider small portion of the disk. This has small thickness dr. So the surface, because it's equally because the charge is equally distributed over the surface of the disk. So if I first I consider small portion, small surface, so the length of this, if I consider this from here to is r, the circumference here be 2 pi r. So circumference into the thickness will give me the surface. So this, if you multiply circumference with dr, that is the small width here, so I get the surface here. So I define the charge density will be dq over small surface, that is 2 pi r into dr. Then I can say the small charge along the surface will be sigma into 2 pi r into dr. So here dv will be k dq by r, similar then as we are doing that. So dv is k is sigma 2 pi r dr over r square plus z square, because this is dq, this is r, just like that. So now we need to integrate, because you are running from, because dr is the integrating factor, it is running from 0 to capital R. So we are integrating 0 to r k sigma 2 pi r dr r square plus x square, because r is a variable here, so this all contribute. So we are taking k into sigma 2 pi, we can take it out, this is a constant. So integration running from 0 to r dr square root r square plus z square. So here this integration you can practice by substitution. What are the things you should do? Because we can to make the integration easier, I will represent, let's say u here is r square plus z square. Then if I du, if I differentiate this will give you r square, so 2 r dr, this is a constant, this is a constant, length is constant, so this will give you 0. From here I can say dr will be equal to r dr, that is here, that will be equal to 1 by 2 du. So I can and actually had to check the limit, how the limits goes. R is here, here is r square plus z square is taken as u, and then what you do actually here, when r equal to 0, when r equal to 0, this become z square, you become z square. Then r equal to r, this become r square plus z square. Then you need to integrate this. So if you integrate, actually this will become 2 pi sigma pi, and this will go from limit, lower limit is z square plus r square plus z square. Then this will be, here rdr is 1 by 2 du. The square root of this will be 1 by rdr will become 1 by 2 du. Then this 1 by this will become 1 by square root of u. So then you integrate, this is pretty easy integral, then you can try this. 2 pi sigma into k, 1 by 2 you can take it out, then it will become z square into r square plus z square into du over square root of u. So this is now easy integral, because your integration of root x like that is, so it will be, you can say that if you take only this part, this is integral u raised to minus 1 by 2 du. So this will give you u raised to minus 1 by 2 plus 1 over minus 1 by 2 plus 1. That will give you u raised to 1 by 2 over 1 by 2. So this will come true. This is 2 raised to e raised to 1 by 2. You get this integral if you substitute that. And if you apply all this limit, you get the integration as sigma by 2 pi epsilon 0. Here k is, I also apply k is 1 by 4 pi epsilon 0. You get the integral as square root of r square plus z square minus z. Inshallah, I hope you understand this, and you can try more examples in Epic College Board and try utilize your integrating skills, and you understand doing potential is more easier than doing electric field. Hope you understand. If you have any doubts, you can post that here or you can ask me directly. Thank you.